So, we have seen that the family of regular sets is closed under the following operations. The family of regular sets is closed under union, concatenation and star. This we proved using regular expressions, right. Then we also saw that it is closed under intersection and complementation. Usually these three operations are considered together and these three operations, set theoretic operations, are considered together. So, anyway, this union is counted in both the sets. Now, we will consider two more operations, reversal and derivative with respect to a string. What do we mean by this? We will come to that in a moment. First, take the reversal. If W is a string A1, A2, AN, the reversal of W, WR is taken as AN, AN minus 1, A1. Okay. If L is a language, then the reversal of L is denoted as LR, and that is the set of WR, W belongs to L. The reversal of a language is take each string in L and then reverse it. Okay. It consists of all strings of the form WR where W belongs to L. For example, if I take L, I will take this example A power n B power m. This I have been considering several times because it is a good illustrative example. L is equal to A power n B power m, n m greater than or equal to 1. This is a regular set. L power r, take each string and reverse it. Okay. So, this will be B power m A power n, n m greater than or equal to 1. What we want to show that is if L is a regular set, LR is also regular. It is also a regular set. We want to show that. How do you show this? It is very simple. L is represented by, it is accepted by a finite state automaton with a state diagram. It can be a finite state, deterministic finite state automaton, non-deterministic finite state automata or non-deterministic finite state automata with epsilon, does not matter. And without loss, you assume that there is only one start state and one final state, because otherwise you can add epsilon transitions and make only one final state. Right. So, have a finite state automaton with epsilon transition. If there are more than one final states, create a new final state and have epsilon transitions leading to that, right. So, without loss of generality, assume that there is only one final state and one initial, of course initial state is 1. Now, how can you accept LR? Any string in L will take you through a path from Q0 to Qf. Now, the reversal, you have to go from Qf to Q0, right. And then in this diagram, if there is an arc like this from one node to another node, change that arc, change the direction of the arc. Keep the same diagram, each arc if it is directed this way, make it directed this way. And make this as the final state, make this as the initial state, right. So, if a string takes you from q naught to qf in the original diagram, in the changed diagram it will take you from, because the arcs are all directed in the opposite direction, it will take you from qf to q naught by traversing to an minus 1 and so on, right. So, this is a transition diagram or a non-deterministic FSA with epsilon moves. So, obviously it accepts a regular set. You can convert it into NFSA and then DFSA, right. Take this simple example which you have considered, q naught, q1, q2, a power n, b power m. I need not draw the dead state. I will tell you why it is not necessary, but if you want you can even draw the dead state, does not matter. Okay, I will draw the dead state, but actually you can omit that also. Dead state B, A, comma B, right. This accepts a power n. Now, I want to convert this diagram so that it accepts b power m, a power n. So, reverse the direction of every arc, self loop will be same, make this into initial state, make this into a final state. Initial state, in this example it so happens that you have only one final state and one final state. If you have more final state, you must create a new final state and draw epsilon arcs. So, now you can see that it will accept b power m, a power n. This is not really required. The reason is, note that this is a non-deterministic FSA. What you have obtained is a non-deterministic FSA. From B if you get, from Q2 if you get a B, you can go to Q2 or Q1. From Q1 if you get a A, you can go to Q1 or Q0. So, what you are getting is a non-deterministic FSA, but you know that you can convert a non-deterministic FSA into deterministic FSA. This is not at all necessary, because from D you can reach any state, but starting from the Q2 you cannot reach D. So, it is not going to contribute to anything, right. So, this is not necessary, you need not have considered this portion at all, that is not going to affect the result in any way. Okay. So, we know that if L is a regular set, LR is regular. So, the family of regular sets is also closed under reversal. Now, one more thing we have to consider, which will be used for converting a regular expression DFSA into a regular expression. X belong to sigma star. X is a sum string. We are considering the alphabet sigma, and X is some string, and L is a language. L is a language. We denote by L of X, L with a subscript X. this is called the derivative of L with respect to x. What is this language? This is the set of strings of the form y where xy belongs to L. That is, in L you take strings which begin with x, x is a string. So, consider from L the set of strings which begin with x and remove that x portion. Okay? Is that clear? Let us see some example. 0 0 0 plus 1 star 1 1, or let us consider the example which we considered yesterday. Set of strings beginning with A and ending with B. The regular expression for that was A plus B star B, is not it? This is a regular set. Now, what, suppose I denote it by L. L is represented by this, that is the set of strings over A and B which begin with a A and end with a B. Now, what can you say about LA, the derivative of L with respect to A? You take all strings beginning with A and remove the first A. So, what will be that? That will be just this, any string of A's and B's ending with the B, is not it? So, L of A will be set of strings ending with B, that is all. It will be represented by A plus B star B, and you know that it is a regular set. Now, if you take L to be this A power n B power m, n comma m greater than or equal to 1, what is L of A? What is L of A? A power n B power m, yes, n greater than or equal to 0, m greater than or equal to 1. What is L of B? There are no strings beginning with B. So, L of B is empty. Okay. Now, you can see that we are taking L, L of A is a regular set. Here also there are, if you take L, L of A is a regular set, L of B is also a regular set, phi empty set is a regular set. Now, what we want to show is X is a string in sigma star, L of L is a regular set, to show L of X is regular. The derivative of L with respect to S is a regular set. How do, it is very simple. How do you show that? take a deterministic diagram without loss of generality, L is accepted by a DFSA. Then what change? L is accepted by DFSA M, some diagram with one initial state, maybe some final states. Now how will you get L of x? Make? Yeah. The same diagram you can have, remove the initial state, starting from here, go through a path for x, you will reach some state, make this the initial state, that is all. Okay. Start from the initial node, go through the path corresponding to x, you will reach one state. I am taking a DFSA. If it is NFSA, there will be many states and so on. So, I do not want, I mean, for simplicity I am taking a DFSA. So, starting from Q naught, after reading x I go to a particular state, only one state, right, make this the initial state. Same diagram, but you are making this the initial state. If the original one accepts something like xy, this automaton will accept y. So, this change diagram will accept, it represents a DFSA which will accept the derivative of L with respect to x, right. So, what do you get? If L is a regular set, L of x is regular. Okay. I have taken a string. Now, say I take a regular set L, I consider L x1, L x2, L x3, L xn like that for different strings. How many distinct derivatives can I have? Okay. For let us take this example. L is a power n, b power m. L of a is a power n, b power m, n greater than or equal to 0, m greater than or equal to 1. What can you say about LAA? What will be LAA? Same as LA, right. What can you say? LB is empty, LBB will also be empty, right. What can you say about LAB? What is LAB? B power m, right. Okay. So, this is one a power n, b power m, n greater than or equal to 0, this is one derivative, this is one derivative, this is one derivative, empty set and so on, right. Now, similarly for anything Lx1, Lx2, Lx3, Lxn are some derivatives. How many of them? After some time they have to be equal, right. How many distinct derivatives can you have? It depends on the number of states. See, while for considering L of x, I am making this into a initial state. Similarly, I can make each one of the states, the greatest possibility is each one of the states can be made as the initial states. So, if there are n states in the DFSA, at most there will be n distinct derivatives. Afterwards, they will become equal. more and more strings you consider, some of them will be equal, right. In this diagram I can make each one of the states as the initial state and get a regular set, right. So, for x1 I may make this as the initial state, for x2 I may make this as the initial state, but again for x3 I may make come to this itself, is not it. So, at the most I can have n distinct derivatives. Okay, this we will use now. We have considered this given a regular expression, how to construct a NFSA with epsilon mu. This we consider. Now, today we shall consider given a DFSA how to find the regular expression. I will recall one theorem which we studied in the last semester, this lemma or theorem, whatever it is. We studied this in the last semester, please recall this result. If epsilon does not belong to A, x is equal to Ax plus B has a unique solution, x is equal to A star B. Did we not study this? How many of you remember? Okay. So, we will make use of this. I will assume this result. If you have forgotten the proof, please go through your notes and remember, try to remember. If epsilon belongs to A, the solution will not be unique. A star B will still be a solution, but it will not be unique. So, we will not bother about that because this is the result we will make use of. So, now our aim is given a DFSA, how will we construct the regular expression. Again I will start working out with an example. We will work two or three examples. The method should be clear, and while working out we know that the procedure is correct. Give the argument that the procedure is correct. So, let me start with this same A power and B power. How many states are there? There are 4 states. So, for 4 states I will write 4 equations. Okay. How do you write the equations? Okay. First start with Q naught. Q naught equal to, it goes to AQ1. So, AQ1, starting with the B it goes to D. Q1, but okay, Q1 is AQ1 plus BQ2. Q2 is AD plus BQ2. But if it is a final state, you must add one lambda also, lambda or epsilon. I will use lambda for empty string plus lambda. This denotes the empty string. Then D is equal to AD plus straightforward how you write the equations. I am starting with the deterministic capacity. So, it is very simple how you write down the equations. You must look at these as unknowns. In essence, you are having 4 unknowns and 4 equations, and you must be able to solve. But the thing is, they are not simultaneous equations as you studied earlier, they are equations involving regular expressions. So, you have to use a different technique, and the technique you use is you will be making use of this lemma. Only 2 things you use in solving. You have to solve for q naught. Q naught is the initial state. So, there are 4 equations with 4 unknowns essence. You should be able to solve them, and for solving that you use 2 techniques. One is substitution, another is this lemma, only these 2. So, let us see how to solve this. First take d is equal to AD plus BD, and that you can write as A plus B D. Okay. I can write it as A plus D plus phi. Can also write it that way, is not it? Now, this is of the form d is equal to A plus B D phi, right. So, actually it is of this form, is not it? So, you can solve for d, use this lemma. It is of the form x is equal to Ax plus p, and epsilon does not belong to this. So, use the lemma. What will be the solution for d? What will be the solution? A plus b is, right, and something concatenated with phi is phi. See, you have this result. This also we studied earlier, L phi is equal to phi, L is equal to phi. But what is phi star? This again you must remember, phi star is not empty, it is having one string. Phi star is epsilon. Why? Why phi star is epsilon? Phi star union of I is equal to 0 to infinity phi I. So, it will be phi 0 union phi 1 union etc. All this will be empty, but phi 0 is epsilon by definition, right. Okay. Okay, before proceeding further, what will be the answer you have to get? It represents a power n, b power m, a power n, n, b power m, n greater than or equal to 1, m greater than or equal to 1. What will be the regular expression? You have to get this answer, is not it? A star, b star, is not it? This is the answer you have to get. So, let us see how whether we get it. D is empty. So, when D is empty, this will become empty, this will become empty, right. So, the equations will now reduce to Q naught is AQ1, Q1 is AQ1 plus BQ2, Q2 is BQ2 plus lambda. Now we have got rid of one equation and one unknown. So now we are ending up with 3 equations with 3 unknowns. Now each time when you do the substitution or solving, after that you must get rid of one unknown and one equation. Now look at the last one, it is again of this form, right. So what is the answer for Q2? Q2 is B star lambda, that is B star. Now use this in the other equations, use this in this. So what do you get? You get Q1 is equal to A Q1 plus B, instead of Q2 you write B star. Now we are having only these 2 equations. So we have got rid of one more unknown and one more equation. We are having 2 equations with 2 unknowns now. So again this is of the form Ax plus b, right. So what will be the solution for this? Q1 will be A star B B star, isn't it? This star followed by this. So this is A star B B star. Use this in the first equation. Q naught is A Q1, that is A star B. So solving for Q naught you have got the answer. Okay. Now this method will work because each time we are trying to get rid of one equation and one unknown, and we are using either that lemma or substitution, right. So finally we should be able to solve for Q naught. Now why we do this and what is the underlying meaning behind this, why we should do this. Okay. Now when you solve for D, D is empty. When you solve for any variable here, take for example Q1, what is Q1? Q1 is A star B B star, isn't it? Finally you got this, Q1 is A star B B star. It is a set of strings which take you from that state to a final state. So the set of strings which take you from that state to a final state is represented by that when you solve for that variable. So D means the set of strings which take you from D to a final state, but no string takes you from D to a final state, it is empty, right. So you are getting the empty state, D is empty. Q2 represents a set of strings which take you from Q2 to a final state. What is that? You can go through this several times. So B star. So when we solved, what did we get? Q2 is B star. Q1 is the set of strings which take you from Q1 to a final state. So that will be A star B B star, that is what we have got for Q1. Q naught is a set of strings which take you from Q naught to the final state. So that is, you know that it is A star B B star. Finally we have to solve for the initial state. See, suppose I have say 10 states or something like that, you will get 10 equations, but then you have to be, while solving you have to use your sort of intuition. You must try to get rid of quite easily how, in which order you will proceed, which one you will try to remove first. That is not, there is no hard and fast rule, you have to look into the rules and then try to see which one you can get rid of easily and then solve. Finally you have to solve for the initial state, that represents the set of strings which take you from an initial state to a final state, and that is the answer you want. Okay. Now how are we justified in writing this equation? and what is Q1, what is Q2 and so on. We are justified in writing this equation because of that. In reality, you can see that Q naught represents L, the language, Q1 represents LA, the derivative of L with respect to A. Q2 represents LAB. Right. So, the first equation Q naught is equal to A Q1, D is of course LB. Q naught is A Q1 plus B Q2, this is what we have written. Instead of, I can write L is equal to A LA plus B LB. This is what we have written, and anything for that matter, some L, some A or something like that on the left hand side, you write it as A AA plus B AB, you write like this. What does that really mean? This represents a set of strings. It represents a set of strings which take you from a particular state to a final state. Now, in this place, so here for example, Q naught represents the set of strings which take you from Q naught to a final state, right. Now, this represents the derivative of A with respect to A, okay. So, the set of strings, some of them can begin with a A, some of them can begin with a B. A is a set of strings, right. Among the set of strings, some of them will begin with a A, some of them will begin with a B. So, this represents the set of strings which begin with a A. Set of strings which begin with a A is A, then the derivative of A with respect to A, is not it? And the set of strings which begin with B is this. For example, here you see Q naught represents the set of strings which take you from Q naught to a final state. If among them, some of them may begin with a A, some of them may begin with a B. This represents the set of strings which begin with a A. This represents the set of strings which begin with a B. That is why it is empty, no string. In this case it is empty because no string begins with a B, right. So, we are justified in writing like this. This equation is really this, and the next equation is Q1 is AQ1 plus BQ2. That is LA is ALAA plus BLAB. But we saw that LAA is the same as LA, isn't it? So, this is an LAB, LAA is the same as LA, this we have earlier seen. Somewhere we have written. LA is this, LAA is also this, LB, LBB they are all empty. LAB is equal to B power m, m greater than or equal to 0. If you consider LABB, this is also the same. Set of strings beginning with ABB and then remove the ABB. It will be B power m, m greater than or equal to 0. So, continuing our equation, LA is the same as LA, this is LAB. Then the third equation is Q2 Q2 is AD plus BQ2 plus lambda. This is as L, Q2 is LAB, LAB is A, LABA plus B, LABB plus lambda. And this is again empty because string starting with ABA is empty here. So, this is A5 it will be, or LB again, this will be empty, and this is just LAB itself. Okay. And this equation D is equal to AD plus BD really represents LB is equal to ALBA plus BL. So, we are justified in writing the equations in that manner. And by this lambda here, this really this Q2 is equal to, where is that? Q2 is a set of strings which take you from Q2 to a final state. Some of them may begin with a A, some of them may begin with a B, but those beginning with A are empty, that is why this becomes empty. Some of them may begin with a B, that is why you get this. But if it is a final state, the empty string also takes you from that state to the final state, isn't it? So, in order to accommodate for that, from Q2 you have a set of strings which take you from Q2 to a final state. This accounts for the set of strings which begin with a A, this accounts for the set of strings which begin with a B, and this accounts for the empty string because it is a final state. You are not adding lambda anywhere. If it is not a final state, you are not adding lambda, right? If it is a final state only, you are adding lambda. This is the explanation why we are justified in writing such equations, right? So, given a DFSA, you can construct the regular expression in this. First, in this manner. First, you write n equations with n variables. Because you have n equations with n variables, you will be able to solve. And the two techniques which you use are substitution and this lemma. And both, while substituting, you are justified in substituting, and while using this lemma also, you are justified. So, finally, you get the correct solution. That's all. Okay. So, let me take one more example and solve. Zero, 1. Look at this diagram with 3 states. L is a set of strings over 0 and 1 accepted by this FSA. Is this a deterministic FSA? This is a deterministic, and this solution works for a deterministic FSA, not considering the non-deterministic FSA. That is why you are able to write uniquely the next thing, right. So, let us find the regular expression. What sort of strings will be accepted by this machine? One condition will be the string has to end with what sort of strings will be accepted by this machine, or what sort of strings will not be accepted by this machine. The string has to end with a 0. Epsilon will be accepted of course, but apart from that any other string it has to end with a 0. Let us find the regular expression corresponding to this DFSA. So, how do you go about doing that? Let us first write down the equations. Q naught is 0 Q1 plus 1 Q2 plus lambda, because Q naught is the final state, and equation for Q1 will be Q1 is 0 Q1 plus 1 Q2, right, and Q2 is 0 Q naught plus 0 Q naught plus 1 Q. You have to solve for Q naught, right. As I told you, you have to look into the equation and try to solve whichever is easier and so on. So, take this, from this you will get Q1 is equal to 0 star 1 Q2 right. Use that here. Q2 is equal to 0 Q naught plus 1, instead of Q1 you write 0 star 1 Q2. Use this in this equation, you will get this, right. So, that will be Q2 is 1 0 star 1 Q2 plus 0 Q naught, right. Use the lemma again. So, Q2 will be 1 0 star 1 0 Q naught. Right. Look at the first one. Q naught is 0 Q1 plus 1 Q2 plus lambda, that is equal to 0. Q1 is 0 star 1 Q2. So, 0 star 1 Q2 plus 1 Q2 plus lambda, that is 0 0 star 1 plus 1 into Q2 plus lambda. But what is Q2? Q2 is 1 0 star 1 star 0 Q naught. So, use that here 0 0 star 1 plus 1, instead of Q2 you write this 1 0 star 1 star 0 Q naught plus lambda. So, Q naught is this Q naught plus lambda. It is again of the form x is equal to A x plus b, where b is lambda. So, if you use the expression, if you use that x is equal to Ax plus b is A star b, you will get 0 0 star 1 plus 1, 1 0 star 1 star 0 star lambda. This is nothing but that lambda you can remove, 0 0 star 1 plus 1, 1 0 star 1 star 0. That is, starting from q naught, how will you reach q2? 0 0 star 1 or just 1, right, that is this portion. Starting from q2, how will you get q2 again? q2 1 0 star 1, that you can repeat several times, that is why that 1 0 star 1 star is here. Then you go back to 0 q naught, and this itself we can repeat several times, and that is why the star outside. Now, you can see that apart from epsilon, the string will end with a 0, it cannot end with a 1, and then each time a string within the bracket is considered, there will be 1 1 contributing from this and even number of ones contributed from this. So, always the blocks of 1 will be of odd length, they will not be of even length, right. So, this method helps us to get the regular expression from the finite state automaton. So, for a regular set, we have, this is complete now, you have DFSA, you have NFSA, you have NFSA with epsilon moves, and you have regular expressions. So, we have seen, given an NFSA with epsilon move, how to construct the NFSA without epsilon moves, and by subset construction from a NFSA you can construct the DFSA. Given a regular expression, you can construct the NFSA with epsilon moves, this also we have considered. And today what we have considered is, given a regular expression, how to find the, given a DFSA, how to find the regular expression. So, regular sets can be represented in 3 different ways, 3 ways to represent a regular set. One is grammar, it is type 3. Second is FSA, which is an acceptance device. We have shown the equivalence between the two earlier, and another is by means of regular expressions. We have seen the equivalence between these two now. So, all these 3 are different ways of representing a regular set. The idea of regular expressions is very useful in LEX. LEX is a automatic lexical analyzer generator, which is used as part of a compiler generating device. The compiler has 2 parts, the parser and the syntax part and the analysis part and the synthesis part. The analysis part consists of the lexical analyzer and the parser, and nowadays you have automatic way of generating the lexical analyzer and the parser. You have a program called LEX, which is a automatic lexical analyzer generator, and you have a program called YAC, which is automatic parser generator. A lot of context free grammars and parsing ideas will be used here, lot of regular expressions idea will be used here. I will spend maybe a few minutes on this sometime later, how the lex works, or the idea behind the automatic lexical analyzer generator. Not only that, in text editors also the idea of regular expression is used. That is for pattern matching. So, you want to see, you have a big text, in the spell check and all you use this quite often. You have a text and you want to find out, supposing you have misspelled something, you want to check what is that word and then check wherever you have that word, you have to replace it by the correct spelling and so on. Okay. So, for example, something like theory, instead of writing like this, you have written like this somewhere, you will check and then replace it, right, and just or for that matter some name you have misspelt, then use the spell check, you use the spell check. What it uses, ultimately it uses some idea of a regular expression or a finite state automata. Okay.